Hello everyone, welcome to our ACCV paper presentation. My name is Zhang Yojia. Today I'm going to present our work on Spatio channel attention blocks for cross-modal crowd counting. This work is done in collaboration with Choi Soyeon and Dr. Hong at Inha University. Crowd counting is a core and challenging task in computer vision, which aims to automatically estimate the number of pedestrians in unconstrained scenes without any prior knowledge. In general, the various approaches for crowd counting can be roughly divided into two categories: detection-based methods and regression-based methods, driven by real-world applications, including traffic monitoring, social distancing monitoring, and other security-related scenarios. Crowd counting plays an indispensable role in various fields. Due to the limitations of methods or insufficient data sources, most previous works have focused on RGB crowd counting and failed to obtain high-quality density maps in unconstrained scenarios. With the development of different types of sensors, they can supply RGB images with rich complementary information. As shown in Figure A, thermal images are robust to bad illumination, and depth data naturally complements RGB information by providing the 3D geometry to 2D visual information. However, as shown in Figure B and Figure D, thermal and depth data will also introduce non-negligible noise. So, in this study, we focus on two main issues. First, crowd counting data is obtained from the different modalities, which means that they vary significantly in distribution and properties. Since there are substantial variations between multimodal data, how to effectively identify their differences and unify multiple types of information is still an open problem in cross-modal crowd counting. Second, constructing a cross-modal model architecture from scratch usually entails a lot of trial and error. If the widely used RGB-based unimodal architecture can be extended to multimodal architecture without bells and whistles, we can relieve the effort of design choice of the model architecture. In this paper, we propose a novel plug-and-play module called CSCA block, which can significantly improve performance when integrated with any RGB-based crowd counting model. We proposed a unified framework to extend the existing baseline models from unimodal crowd counting to the multimodal scene. As shown in the figure, the framework for cross-modal crowd counting consists of two parts: modality-specific branches and the CSCA block. Given pairs of multimodal data like RGBT or RGBD pairs, we first utilize the backbone network to extract the modality-specific features of RGB images and thermal images. To fully exploit the multimodal complementarities, we embed CSCA after different convolutional blocks of the two modality-specific branches to further update the feature maps and get the complementary fusion information. To ensure informative feature interaction between modalities, our CSCA consists of two operations: spatial-wise cross-modal attention block and channel-wise feature aggregation block. The SCA block utilizes an improved cross-modal attention block to model the global feature correlations between RGB images and thermal or depth images, which has a larger receptive field than the general CNN modules and facilitates complementary aggregation operation. A typical non-local block is shown in the left picture, which aims to capture the global relationships among all locations of the input image. However, the typical non-local block can only work on unimodal data, and the high complexity introduced by matrix multiplication hinders its use. To alleviate these problems, we propose the SCA block. Different from the typical non-local block, the input of our SCA block is a pair of images with different modalities, and its key and value are from the same modality, while the query is from another modality. Thus, the SCA block aggregates and aligns the information from two modalities. To address the problem of high complexity consumption, some works reduce the dimensions of the key and value through the pooling operation. But it is hard to ensure that the performance would not degenerate too much by losing a lot of global information. Instead of the pooling function, we perform reassembling operations in the SCA block to randomly divide the feature map into GL patches in the spatial dimension. Finally, we recover the channel dimension and reshape the result to the original size. Therefore, the computational cost of our SCA block is GL times less than the computational complexity of a typical non-local block. To complementarily aggregate cross-modal features according to their characterization capabilities, we propose a CFA block to fusion the cross-modal features and capture channel-wise interactions. The CFA includes the following 4 steps. Through the CFA block, the network can increase sensitivity to informative features on the important channels and enhance the final feature map. Hence, the module can adaptively provide more discriminative and richer characteristics to increase cross-modal crowd counting performance. To evaluate our method, we carry out detailed experiments on two cross-modal crowd counting datasets, RGB-TCC and Shanghai Tech RGB benchmarks. To evaluate the effectiveness of the proposed CSCA module, we easily incorporate CSCA as a plug-and-play module into backbone networks, such as MCNN, CSRNet, and BL networks. We report the result in Table 1 and Table 2. In conclusion, all experimental results confirm that CSCA is universal and effective for cross-modal crowd counting. Moreover, our model also achieves better performance on the RGB-TCC dataset compared to specially designed crowd counting models. Especially, our CSCA implemented with the BL backbone achieves state-of-the-art performance on almost all evaluation metrics. Similarly, our model implemented with the CSRNet backbone outperforms most advanced methods and achieves a new SOTA result of 6.39 in RMSE. From Table 5 and Table 6, we can observe an interesting finding that thermal images are more discriminative than RGB images for the RGB-TCC dataset. However, RGB images are more efficient than depth images on Shanghai Tech RGBD. Interestingly, naive feature fusion strategies such as early fusion and late fusion even damage the original accuracy. Moreover, every component is essential for our CSCA. As shown in Table 7, we conduct experiments under bright and dark scenes, with 3 different input settings, including unimodal RGB images, unimodal thermal images, and RGBT multimodal images, respectively. It is easy to conclude that our CSCA can complementarily fuse thermal information and RGB optical information. From the visualization results in cases A to D of this figure, we can easily find that thermal images can facilitate the crowd counting task better than RGB images. As we discussed earlier, inappropriate fusions fail to exploit the potential complementarity of multimodal data and even degrade the performance, such as the early fusion and late fusion shown in Case E and Case F. Our CSCA achieves significant improvements for cross-modal crowd counting by simply integrating into the backbone network. As shown in Case G, this qualitative result shows the effectiveness of CSCA's complementary multimodal fusion. Please check our paper for more details and results. If you have any questions, you can visit our lab webpage or contact me via email. Thank you for your attention.